All right, a few final issues to close out this section. Some of the null hypothesis testing strategies that we will encounter in this class, and it's a lot of them. We start off with the z-test. It's a great introduction, not very useful. One of the things we'll see is that z is problematic because you have to know the population standard deviation, and we don't actually ever really know that. Next up is what's called the t-test. Looks a lot like the z-test. 90% of the stuff that we learn about the z-test is applicable to the t-test. There are going to be 3 different t-tests, so we'll spend a fair amount of time on the t-test: one sample, independent samples, and paired t-test. Then we'll get into something called ANOVA, one of the biggest topics in the class. You can take an entire course on ANOVA if you want. In fact, next semester, I'm teaching an entire course on analysis of variance. That's how large a topic it is. Actually, regression, multiple regression, correlation, those all have hypothesis testing aspects in them that we'll circle back to. But there's a hypothesis testing approaches built in there. And then the final topic that we talk about in this class, chi-square, another hypothesis testing approach. So one thing you can see is pretty much all of the class is hypothesis testing from here on out. Any procedure that leads to a conclusion about whether you can make a decision about a hypothesis or not is a hypothesis testing procedure. And these really are the heart of what evidence looks like in psychology. These are the procedures that make things go. A couple other issues that I don't think are very important, but you will see them get a lot of coverage in some sources. Directional versus non-directional tests, or two-tailed versus one-tailed tests. We use a two-tailed approach because it can produce a confidence interval, whereas a one-tailed test cannot. Some people sometimes argue for use of a one-tailed test because they only care about effects in a certain direction. So you'll occasionally see those used. Another issue here is using different alpha values. We just use 0.05 here, but it's not hard to convert to a different value. If you're using 0.01, then you would only reject the null if your result happened less than 1% of the time. This would correspond to a 99% rather than a 1% confidence interval. Again, different people will do different things, so don't be surprised if you see other values at work. All right, statistical decisions and statistical power. Power is the probability of rejecting false null hypotheses. And while we can set our alpha level, it's much harder to set our level for beta. There's a lot more that affects our level of beta. Alpha, we simply just say, hey, I'm using alpha 0.05. All right, good. With beta, there's multiple factors at play that influence beta. So I'll talk about this a little bit differently, the factors that influence power, or 1 minus beta. There's a little acronym I learned in graduate school, BEAN. So if you're a vegetarian, you should be very interested in this. B is beta. 1 minus beta equals power. Well, we don't really need the B, but there's no acronym without it. E, effect size. That's getting into how large differences we have. How big are the differences that we're exploring? How much different is my sample result from the value in the null hypothesis? Effect size, bigger effects, more prominent effects, bigger differences mean more power. And we'll see later in the semester, we'll have a number of different estimates of effect size. Basically, the simplest way to think about this is how big is the difference over the standard deviation, which is actually just a z-score. Correlation, proportion of explained variance, those are also measures of effect size that we've worked with. Alpha, as alpha goes up, as our tests become more liberal, and this is liberal in the sense that it's easier to reject the null hypothesis, not liberal in the sense that you're going to vote for Joe Biden. As our alpha value goes up, we get more power. As we make it easier to reject the null hypothesis, we're more likely to reject the null hypothesis. Sample size. Sample size is probably the most important one. Bigger sample sizes mean more power. We saw in the previous section, bigger sample sizes mean the standard error of the mean is falling. That is where we're getting that increase in power. Less error in our estimation, more power to detect effects when the null hypothesis is actually false. In general, you can always specify 3 of these and calculate the other. Most commonly, what people do is they specify alpha, effect size, and beta to find a desired sample size. All right, some issues with power. Type 1 error rates or alpha rates are really easy to control. We just simply say, bam, that's your type 1 rate. Type 2 rates are a lot harder to control. In fact, within psychology, it's estimated that we run at about a 40 to 60% type 2 error rate, which is clearly massively much larger than the alpha rate. So much more common way to make an error is to have a false negative rather than a false positive. All right, if you'd like more information about statistical power, this book is pretty good. I highly recommend it. It's Applied Power Analysis for the Behavioral Sciences by, what's the author? Oh, Christopher L. Aberson. At wherever you find your fine books.